On this episode of MRI Physics Explained, we begin our journey on understanding MRI pulse sequences, starting with a deep dive on the echo. You've all heard of this term, so how does it work? How are we able to make our signal reemerge, and why does this even work in the first place? We're going to push the boundaries of knowledge on this subject, as well as my amateur animation skills, as we take a deep dive into a long-neglected topic on the latest episode of MRI Physics Explained. Welcome back everyone, and hello to all of our new viewers. If you like these lectures, please like and comment. Follow us on social media for additional content and previews, links in the description below, and click that subscribe button. Also, check out our new membership section by hitting that join button next to the subscribe button below. We appreciate all your support, and that's what keeps this channel going. With that, let's begin. Now, when discussing pulse sequence diagrams and echoes, the underlying concept centers on how signal evolves over time. Now, if you followed the lectures up to this point, you know that we start this process of generating signal by means of an RF pulse applied here at time 0. This generates our initial signal within our receiver coils, which we call our FID or free induction decay. As you've learned in the previous lectures, this alone is not enough to generate an image coming from a slice of the body. We first needed to develop a way to selectively excite protons in a single slice of the body, which we do by applying our slice select gradient at the same time we apply our RF pulse, at time 0. Now that we're generating signal from our slice of interest, we have to find a way to localize the signal at each point in the slice to build a picture. And we did this by applying our frequency encoding gradient and phase encoding gradient. And here is where we hit our first stumbling block. We have two gradients we need to apply, but only one signal, our free induction decay. And in the phase encoding lecture, we showed why we can't simply turn both of them on at the same time. We'll discuss why the phase encoding gradient looks funny in the next lecture, but ultimately we need to pick one, so the gradient that is applied to our initial FID signal and changed throughout the sequence is designated our phase encoding gradient. So we've come to the point you've all been waiting for. We now need to develop a way to make this signal re-emerge so we can apply our frequency encoding gradient, and we call this re-emergence the echo, as I'm sure many of you have at least heard of this term before. So the question is, how do we do this? How would we go about getting this signal to re-emerge? A natural thought would be to apply another RF pulse. We did it over here to produce this signal. So what happens if we simply apply another RF pulse at some time point after our FID has dissipated? Again, applying our slice select gradient at the same time to ensure that all the energy from the RF pulse is focused on our slice of interest. Let's try to visualize what may be going on at the proton level within our slice. Let's say this is the slice of interest we're trying to image, a complex looking slice through the head. Within the scanner, this slice is sitting within the XY plane. Our Z-axis is going into and out of the screen, and you can see one of our receiver coils paralleling the Z-axis. If we take a look at this from the side, it'll look like this, with our B0 magnetic field running in this direction along the Z-axis. So looking back at our slice, staring down the bore of the MRI machine, we have our slice experiencing a constant magnetic field B0 at this point. If we pretended this whole slice was one giant voxel and added up the total net magnetization of the entire slice, we would generate one big net magnetization as shown. But we can equally break this slice into 4 voxels, and instead of having one big net magnetization, have 4 smaller net magnetizations representing the magnetic vector from all the protons summed together within each voxel. When added together, gives us back our total summed net magnetization of the slice. We can do this process for as many voxels as we like. Let's stop here at 9 voxels. I think this is a good number to highlight what we're trying to visualize. Now we need to make a slight correction. In this picture, our little net magnetizations are aligned in the XY plane, but in reality, they should be aligned with our B0 field along the z-axis in our initial resting state, which would look like this. You can see why we started drawing them the way we did. This is more complicated to visualize, but if we change our view again to the side of the slice, it makes much more sense. So let's go through some of the steps we already know. We'll excite the system with our RF pulse. Let's choose a flip angle of 90 degrees for this example, and when applied, all the net magnetizations from each voxel will be knocked 90 degrees into the XY plane, nicely aligning with our slice. Switching back to our view looking directly down the bore of the MRI machine at our slice, our net magnetizations will look like this, and we know they'll start to precess at the Larmor frequency, in this case B0 since we're not applying any gradients. Now as these rotate, they're going to generate signal within our receiver coil as shown. But we know that they don't stay rotating in sync together, at least not for long. Some of these will speed up relative to one another, some will slow down, and we'll get a degree of dephasing from what we call these T2 effects. So in order to keep things simple, we'll pretend these net magnetizations in the middle will start spinning at different rates. Let's see what happens to our signal now. You can see that the longer these spin at different rates, the more out of sync or dephased they become, and the smaller our signal gets. Just to compare, here is where we started. And here is where we ended up. Notice that the overall size of our magnets within each voxel got smaller, because the protons within it also undergo dephasing as time goes on. If we look at this now from the side, we also see these magnetizations have ever so slightly started relaxing back towards B0. If we continue to follow these magnets as they spin, we'd see something like this. They get more and more out of sync and dephase, subsequently decreasing our recorded signal until eventually it's lost. And that's what brings us to what we know so far, which corresponds to this time point on our pulse diagram. Let's not worry about the gradients right now. So in the past, we would just wait a long time, allowing our protons to realign back with B0 along the z-axis, and then repeat the process, applying another RF pulse, flipping the protons back into the XY plane, and again they spin, generating signal but becoming more and more out of phase due to T2 effects as time goes on. Until our signal is lost. Now, instead of waiting like we did last time for all these little net magnetizations to rebuild along the B0 z-axis, we're going to experiment with this idea of applying a second RF pulse after our FID has dissipated, and seeing how this would affect our protons and net magnetizations, currently in this configuration. So let's apply another RF pulse, and we need to decide how strong to make it. For this first attempt, let's go with a 20-degree pulse. Just to help us visualize things a little better, these now dephased spins within each voxel have an overall orientation like this. Now I know we're using a lot of arrows, and it's tempting to think of this as one large net magnetization coming from all the spins of the slice added together, but remember that we just showed that our spins have dephased to the point that we have no signal. That's why we just see little arrowheads now, and therefore we have no total net magnetization when these are added together throughout the slice. But what they still do have is an overall total orientation, which is still precessing, just not generating signal. So when we talk about flip angle, we're flipping the axis of rotation with respect to the XY plane. In this case, 20 degrees, putting us back perfectly into the XY plane. So let's go ahead and give it a flip. And look back at what the spins are doing in the XY plane. So we've reoriented things a little and given some more energy. What will happen next? Let's watch. The protons will keep spinning, getting more and more out of phase with each other as the T2 effects compound, eventually losing all sense of order, and as you see, no echo is generated. So we're back to square one. We've generated no echo with this technique, and we have to restart the whole process by waiting a long time, letting our protons realign back with the z-axis and fully rebuild our net magnetizations, and then apply our initial excitation pulse to push our system back into the xy plane and generate our free induction decay signal again. So we're back to this point, and we'll once again try to apply another RF pulse, but something has to change as last time it did not result in an echo. So here we are. We've generated our free induction decay and slightly relaxed back towards the z-axis, with the overall orientation of these spins as shown by the white arrow. We're going to apply a second RF pulse, but this time let's go bigger. Instead of a 20-degree pulse, let's apply a 90-degree pulse, which will flip the orientation of all of these spins deep into the other half of the xy plane, as shown. Just to compare for better visualization, here was where we were before the 90-degree pulse, and here is where we ended up after the 90-degree pulse. What happens to our spins and signal now? Looking back at our slice, notice that unlike the previous example, where a very small subsequent RF pulse just led to further spin dephasing, in this case we get what looks to be the opposite, a rephasing of the signal, which steadily grows stronger and stronger as the spins in each voxel become more and more in phase, resulting in bigger and bigger net magnetizations, eventually reaching a peak until the spins in the middle row now get ahead of the rest of the spins and once again become more and more dephased, causing a decreasing signal. So how is this happening? Why did this situation, where we applied a small 20-degree second RF pulse, result in further dephasing and no echo, while the situation where we applied a larger 90-degree pulse resulted in a rephasing of the signal in the form of this echo? There has to be something profound happening between these two instances. What could it be? Let's go back to the first scenario with the 20-degree pulse, and I want you to watch what the spins are doing when viewed in the xy plane. Pay special attention to the direction of rotation each spin and net magnetization is undergoing, and how we get more and more out of phase with time, thus producing no echo. Now let's look at scenario 2 again with a larger 90-degree pulse. Again, pay special attention to the direction of rotation each spin undergoes relative to our receiver coil, and how the spins in the middle row that were before spinning faster, getting further and further ahead of the other spins, are now playing catch-up due to the spin reversal. Eventually catching up with the other spins to produce the maximum signal of our echo, and then once again getting further and further ahead of the rest, eventually leading to more and more dephasing until loss of signal. So is it really that simple? We just apply a large flip angle on our second RF pulse and magically get an echo? What's really going on here? To understand this, we need to put ourselves in the perspective of the receiver coils and ask ourselves, what do the coils see? In this view, looking directly at the side of our slice, we see our receiver coils paralleling the z-axis. Let's hide this set right in front of us just for visualization purposes. And let's drop all notion of phasing and rephasing for a second and just focus on our net magnetization coming from the entire slice and precessing after applying our RF pulse. How does it look to our receiver coil from this point of view? If we draw the path of rotation this vector makes, we get something like this. Now let's apply our secondary RF pulse as in the first scenario, a weak pulse of let's say 20 degrees. It might move our system to look something like this. Again, pay attention to what our coils see. Does it look substantially different than before? This is the equivalent of what we saw in the first case, which resulted in no echo. Now let's try the other scenario and give this a large secondary RF pulse, inverting the spins across the XY plane and into the bottom half. Comparing the before and after, do you notice a difference in what the receiver coil is seeing? Let's try looking at this from one more perspective. This one before the large flip from the secondary RF pulse, and this one after. Comparing the two, notice that by flipping this into the other half of the XY plane, we do in fact change the rotation relative to our receiver coil. Do you remember the right-hand rule in physics? If you curl your hand in the direction of rotation on the top example, notice that your thumb points into the screen. Then do it on the bottom example after the flip, and notice how your thumb now points out of the screen. So by giving a second RF pulse with a large enough flip angle to invert our spins into the opposite half of the XY plane, we're able to reverse the direction of rotation of each spin, and any spin that was spinning faster and ahead of the others will now be behind and playing catch up, over time getting more and more in phase with the rest of the spins, making our signal reemerge as this echo before overtaking the rest of the spins, causing dephasing again, which will make our echo disappear. I know this is really difficult to comprehend and want to provide one more example of this from the real world. How many of you have bought a piece of furniture from IKEA and sat there sweating over those pictogram instructions, trying to figure out where everything goes? Let's pretend you bought this lovely table from IKEA, and you need to attach this bottom shelf to the legs. You manage to crack the code and realize a bolt needs to go right through here. So you get your wrench and rotate it in this direction to tighten the bolt. But suddenly you realize you screwed up. Welcome to the IKEA Self-Assembly Club. You realize the bolt is oriented the wrong way. It in fact needs to be inserted from the bottom. And as most of you have found out the hard way, now staring down at the bottom of this bolt, you cannot just rotate this the same way as before. Frustratingly, everything has been reversed with a simple flip. To tighten this bolt, you now have to turn it the opposite direction as shown. So when the bolt was oriented this way, the direction of rotation to tighten was this. When it inverted relative to the board, the direction of rotation is reversed. If we replace this board with our slice in the XY plane, and these bolts with the axes of rotation of our spins from the prior examples, we can see that indeed flipping our spins into the bottom half of the XY plane does indeed reverse our direction of rotation relative to our receiver coil, illustrated here in our original example. I hope you can now appreciate a way in which we can make the signal re-emerge as an echo, and I want to leave you with a few last important thoughts. First, you can now hopefully see that there is going to be some combination of strength of this second RF pulse and the time at which it's applied that will be most optimal in generating the biggest echo. And finally, notice that compared to our initial free induction decay signal generated when everything was perfectly aligned and in phase, our echo will never reach the same amplitude because we will never be able to get all these spins back in phase again without resetting the whole system and letting it return to our initial maximum net magnetization and phase coherence. And while we used the simplified example of a few voxels and net magnetizations to highlight how this works, the reality is we're dealing with over 1 trillion hydrogen protons on a quantum scale, and it's not as pretty as portrayed. And really, our RF pulse is inverting a statistically significant amount of these spins into the other half of the XY plane, allowing us to recover some of that dephasing that's occurred and generate our echo. So with this knowledge of how we form an echo, we can build our first full pulse sequence diagram and begin our discussion on the spin echo series of sequences on the next episode of MRI Physics Explained. As always, thanks for your support. If you really want to keep these videos going, consider becoming a member or donate using the links below. And that's all, folks. We'll see you for the next episode. This is Dr. TE signing out.